All right, let's get started here. One theorem I want to tell today. So last time we were talking about these graphs from the Hall of Fame. Those were graphs where we could get whatever chromatic number we wanted, and we could be triangle free, were the first two examples. And then the Blanche-Descartes graphs didn't have cycles of length 3, 4, 5. And so I want to talk about a far-reaching generalization of this theorem. Where are we? So this is a theorem by Paul Erdős, about 1959. And it says that if we fix two parameters k and g, there exists, let's say there exists a graph g such that g has chromatic number at least k and girth at least g. Okay, girth has appeared in a homework exercise. Let me just remind you what it is. So the girth of the graph is the length of the shortest cycle. Okay, so length of shortest cycle, which really, for our purposes, more important means there's no cycles of length shorter. Okay, no shorter cycles. Okay, so there's no cycles of length 3, 4, 5, all the way up to g minus 1. Okay. Okay, so we've kind of already proved this theorem in a sense for k whatever, and then g6, right? The Blanche-Descartes graph gives us an example of a graph whose girth is 6. It has no cycles of length 3, 4, or 5, and had any chromatic number that we wanted. The Zhikov graph and the McCleskey graph gave us a proof of this theorem when k was anything and g was 4, right? We had no cycles of length less than 4. Okay. And this is a far-reaching generalization, obviously. So I can pick any two numbers here, and there exist graphs that have these two parameters here. And I mean, I discussed it a little bit last time, but why is this surprising? Okay, why surprising? Okay, well, it's surprising because the graph is locally sparse. G is locally sparse. Okay, what does that mean? If I zoom in on this graph and look at, say, g minus 1 vertices, so any g minus 1 vertices, there's no cycle among g minus 1 vertices, right? So if I grab, say g minus 1 is a trillion, right? So if I grab a trillion vertices, I don't see a cycle among those trillion vertices, okay? So any g minus 1 vertices only are spanned by a forest or a tree, right? That's like, there's no, so any g minus 1's vertices have no cycle. So it's a forest, let's say. But what's really important is that the number of edges there are at most g minus 2, right? So there's about as many edges as vertices everywhere locally. And when you have that few edges or you have no cycles, it means that that set of vertices is bipartite. You can two-color it. So if I look at any trillion vertices, I only need to use 2 vertices for those trillion vertices. Despite this fact, the entire graph needs an arbitrarily large number of colors to achieve the full coloring of the graph, which is pretty interesting, right? I mean, when you zoom in somewhere, so like all of our greedy algorithms kind of like work, I mean, they work globally. I mean, they have to, but they kind of look locally, right? I looked at a vertex and I'm going to color it based on where its neighbors are, what they are, right? That's a local property for the given vertex. But this says even that doesn't matter, that somehow you can construct these crazy graphs that on every trillion vertices, you see almost no edges, but you need, a billion colors still. They exist no matter what, okay? And this proof will be non-constructive, meaning I'll prove the existence of a graph, but I won't construct it for you like we did in Zhikov or McCleskey, where I like literally said, this is the first one and the second one looks like this by building it on top of it. Here we'll prove the existence of this through a probabilistic proof, like we've done a couple times before, where I'll argue with probability that if I construct a graph randomly, the probability that it has this property here is non-zero. And if the probability that such a graph exists of this type is non-zero, then those graphs exist, right? They have to exist. There's no choice for them to exist. They may be rare, but they're out there, okay? All right, And let me mention here, so since this time, so after this was proved, there was a big effort to say, okay, fine, this says they exist, but how do we actually find them? What do they look like? And now there are algorithmic versions of this theorem that actually do construct these graphs, that they can find you graphs with a chromatic number k and girth at least g. So it is possible to construct them. And there are further generalizations of this theorem as well, to directed graphs and things like that. It's of some interest. Mark Kyle, my colleague in the department, another professor in this field, is sort of an expert in this area. So he has some cool theorems on the directed versions of this, which are really nice. Okay, so we'll talk about this one. This is a true gem. This is definitely a step above the other probabilistic proofs we've used before. Like it's the proof's not that hard, but there's a lot more details than before. Okay, so you can also see this theorem as this is an advertisement for the course I'm teaching next semester. If you're interested in the what's it called? The probabilistic method. We'll be talking about proofs of this type all throughout the class. I mean, we'll be focusing on this, and we'll see this proof again as well in there. Okay. All right. So let's start setting up the proof here, and let's just remember what the goal is. We want to force the chromatic number to be high, so we have to figure out some way to do that. And we also want to make sure that there are no cycles of length g. I mean, of length shorter than g. Okay. Actually, if you want, sometimes this theorem can be restated so that you have a strict inequality here and here. I mean, you can put anything you want there. Sometimes it's a little bit nicer. We won't use that. We'll use greater than or equal to, but maybe we'll prove strict inequality the way it comes out. Doesn't matter too much. Okay. So the proof is by the probabilistic method. Okay, so how did that work before? We're going to construct a random graph, and in the following way. Okay, so construct a random graph on vertex set. The vertices are just going to be labeled 1, 2, 3 up to n. Okay, the vertex names are not going to be that important. What happens though, and this is typical when you construct random graphs, the graph we construct is going to be a labeled graph. Okay, labeled graphs are much easier to keep track of the probability of certain structures occurring. So you look at a set of vertices and it's different from a set of vertices somewhere else because of the labels. Now, that's not an issue when you're trying to prove the existence of something, because if I want to prove that there exists such a graph of this type, and the graph that I construct is labeled, well, it still exists as an unlabeled graph, just ignore the labels, right? Like labeling in principle only makes the problem harder for me. It actually makes the probability much easier, but proving the existence of something labeled or unlabeled is immaterial, doesn't matter. It still exists either way, okay? But having labels makes things much easier already for just defining what kind of graphs you can get out of this, okay? So I've got my vertex set, and what I'm gonna do, so for each pair of vertices, add an edge with probability p to be determined. Not too long though. We'll be determining it in a couple lines here. All right. So how does this work? I have some edge probability, and for each pair of vertices, I flip a coin, a biased coin. If it comes up heads, I add the edge. If it comes up tails, I don't add the edge. Okay. We've already talked about this notion, but so the value of p ranges between 0 and 1. If it's 0, then my graph will have no edges. If it's 1, then I'll get a complete graph. If it's somewhere in between, I get more or less edges based on p. Okay, maybe it's even worth saying for 1 second. This isn't relevant to the proof, but the expected number of edges in this procedure here is going to be n choose 2 times p, right? Every one of the n choose 2 pairs of vertices has probability p of occurring as an edge. So the expectation is just this quantity here, okay? So actually, this is nice, right? So p just basically tells you how many edges your graph is going to have, right? If p is a constant, you're going to have like n squared times a constant number of edges. Usually though, p depends on n somehow. Okay, so say I made p be roughly 1 over n, then I'd expect my graph to have about n choose 2 times 1 over n edges, so roughly order n edges, okay? So the determination of p is like what value you decide here has a huge influence on what occurs in your graph. And this will be actually a central theme in the probabilistic method, is just random graphs, how they operate. This stuff's way cool. Okay. But we won't be fiddling with p. We'll be working with specific p here. But I want to think about this for a second, that so what are our goals here for this proof? Okay, or for choosing this probability? Okay, that's really ugly. Goals. Okay, so there's kind of like two goals here. The first is we want to force small independent sets. As we know how to bound the chromatic number of a graph below by the independence number, right? We know this is one of our early bounds on the chromatic number, is that the number of vertices divided by the independence number. Independence number is size of largest independent set. Size largest independent set. Okay, we already know this, but what's the rough reason? If you have a proper coloring of your graph, the color classes don't exceed size alpha G, right? You can't have more than alpha G red vertices, can't have more than alpha G blue vertices, and so on. So if I force my independent sets to be relatively small, this pushes this lower bound up and forces my chromatic number higher and higher and higher and higher, okay? So I want to keep my independent sets relatively small in order to force, to force chi of G large, okay? So what does this suggest about P? If I want to make my independent sets small, what kind of P do I want to choose for that to occur? You don't have to be concrete here, just like what's the rough idea? Ethan?
You want a higher P to.
Yes, exactly. Right. I want suggests P large. Right? Because the larger I make P, the more edges I get. Independent sets become less and less and less and less likely, right? An independent set is a set of vertices with no edge among it. If P is low, then I look at a set of vertices and maybe I don't get any edge there, right? Maybe. But the higher P is, the less likely I am for that set to have no edges in it, okay? So this suggests that P should be large, okay? Now the second goal here is that, so this gets my chromatic number up, but the other thing I want to do is avoid having cycles, short cycles, okay? So actually what I'm going to say here is I'm going to force, I also want to force few, short cycles, okay? Now, instead of forcing no short cycles, I'm going to force very few short cycles because I can deal with short cycles by removing a vertex from them, okay? So the graph that I end up producing here will not exactly have my properties. I'm going to have to do a little surgery on it at the end. Okay, that's very common technique in the probabilistic method. Sometimes you can't get your graph to get what you want, but you can get it close enough that removing things gives you what you want. Okay, so I want to force few short cycles. The short cycles are those of length less than G, right? Because we can delete them later. Okay, and getting few short cycles, what does this suggest about P? P should be small to get this. The larger P is, the more edges I get, the more chances I have to have short cycles or just cycles of any type, right? So there's this like contrast, right, between these two values of P here. Larger P makes independent set smaller. That forces my chromatic number up. That's already was already intuitive to us. How do you get high chromatic number? Certainly edges are helping you do that, right? But if I want to get chromatic number really big, I can just have all the edges, but then I have tons of cycles. Right? So I want to suggest I got to get some sort of P here, okay? So the hard part of this proof is figuring out what P should be, but because I'm telling it to you, I will tell you what P is, right? And like we already figured it out what it should be. But the way that the proof goes is you would imagine, and many treatments of the proof do this, you're gonna calculate expectations for number 1 and number 2 here, okay? And just based on P, unknown P. And then at the very end, you'll calculate, hey, what P satisfies all these equations simultaneously? That'll be the P, right? I'll tell you in advance just so the computation makes it a little bit easier, but very common to figuring these out on your own is leave P unknown, right? Suspend your disbelief for a while, work it out at the end. What's the optimal P that works here, okay? But this is, again, the fact that P, these two competing Ps here is part of what makes this interesting and part of what makes it surprising. Okay, so what's P gonna be? Let's put it in red here. Let's put P equal to, it's gonna be N to the T minus 1, where T is something that's smaller than 1 over G, which is at most 1 over 3. Okay, let's just dwell on this for a second here. G is the Girth value there. So like I want no cycles of length shorter than 100, then t is less than 1 over 100, and p is n to the t minus 1. T is less than 1, right? It's less than 1 over g. And so this minus 1, the exponent here is negative, right? So I mean, this is just the same as n to the t over n. Okay, it's clearly less than 1. Okay, it's just worth knowing in advance. But this form will be handy here because we'll be calculating with this. Okay, so that's our probability. Let's keep it in mind here. And actually, you'll notice I didn't even state it explicitly what it is. T is any number less than 1 over g. I mean, if g is 100, you could take this to be, 1 over 100 minus 1 over a trillion or something like some epsilon, whatever, it doesn't matter. Okay. Actually, there are some versions of this proof that will just set t equal to like 1, what's a common one to do? Like you could set it equal to 1 over g plus 1, for instance, if you just wanted a concrete value. Okay. We won't need that though. We just imagine that you pick any t that satisfies this. Each time you do this, you get something a little bit better in the end result of the proof. I think the n value will end up being a little bit smaller, but that's not something we're worried about. Yeah. So let me backtrack for 1 second here. So notice I'm claiming that this graph exists. I didn't say anything about how many vertices there's going to be. Okay. To get this to work, the number of vertices is going to be pretty large. Okay. So I have to, and we saw this like in the Blanche-Descartes graph and stuff. To get these graphs, we built them up by making lots of copies of them, and n kind of exploded. We had lots and lots of vertices. Okay. There is another interesting question here to say, can I get k, g, and a fixed n? Like do this with a certain number of vertices. Okay. And I think it's actually still open to determine what's the smallest n for which you can guarantee these things here. Okay. But that's not part of our goal today. I don't care about how many vertices. If to get chromatic number 10 and Girth 12, I need 10 billion or 10 to the 10 vertices or whatever, like that's not a problem. We allow that. Okay. In fact, we'll use, so keep in mind that n, the number of vertices, is like a variable. Like we're going to allow it to get larger and larger and larger to make things work the way we want them to. And at the end, we'll just pick whatever n worked for all of them. Okay. This is one of my favorite techniques in combinatorics is construct an object, let n be large. You get all kinds of cool stuff for free by just letting n, like your n value grow. Like stuff happens that's good, because n to the, in fact, I'm literally writing a paper yesterday where it was important, sorry, that n be large enough so that n to the 1/10 be bigger than log n, right? N to the 1/10 is definitely grows faster than log n eventually. Actually, it takes 10, you have to get to 10 to the 10 for that to happen. But if n's growing, just let it be big enough so that happens, right? So like, anyway, all right. So where are we? Okay, we picked the probability. Now let's address these two goals here. I'm going to start with the second one here because it's the easier of the two here. Okay, so let's look at cycles. Let's try and estimate how many cycles we're going to have in this graph with probability p here. Okay, so estimate number of short cycles. We want to have few of them. Okay, so let's draw a picture here. Say we fix a set of vertices. Say there's j vertices. And I'm interested in if there is a cycle on these j vertices or not. To make life easy, let's remember that the vertices are labeled. They have a name to them. So there's lots of potential cycles on these j vertices, right? You could go in the natural order around, you could zigzag all around. I'm only interested in the sort of canonical cycle here that just goes around them like this. I'm only interested in that cycle. If I want to talk about a different cycle, right, that just like goes around inside of here, I would present a different ordering of the vertices and ask, does that ordering of the vertices have a cycle? Okay, does that make sense? So ordering actually helps me here because otherwise it'd be like, oh, I don't know what's the probability. Okay, so what's the probability of getting this very specific red cycle?
So just p to the I.
Yes, exactly. Yeah, Ethan, let's say that's a j there. But yeah, the probability of that is just p to the j, right? Each of the red edges has probability p, and I want all j of them to appear, so probability p to the j, okay? But keep in mind, that's very different from what's the probability of getting a length j cycle among those vertices, right? That's a higher probability because the blue edges or those other things. But I'm talking about the probability of red cycle on these ordered vertices, okay? So there's one instance where having order actually made things easier to compute here. Okay, how many ways can I choose these vertices? So number of ways to pick this set of vertices for, again, j is fixed here, right? So how many ways can I pick j vertices with this order, right? Keep in mind, it's j vertices and it's a specific order of them. Well, it's n times n minus 1 times n minus 2 down to n minus j plus 1. This is an overcount though. So I picked these vertices in this order, but asking whether or not this is a cycle, I could have picked them in multiple ways from this here. I need to divide by something. Any idea what I need to divide? Once you see what we divide by, it's clear that we should have divided by that. But so so divide by j is the first part, right? Because I could have picked first, second, third, fourth, fifth, sixth, seventh, or I could have first, second, third, fourth, fifth, sixth, seventh, and so on, right? Each of those picks would have been a different choice according to the numerator here, but they do ask about the exact same cycle, right? So divide by j, and there's one other thing I have to divide by as well. What else do I have to divide by? Yeah, 2j, exactly. There's a 2 as well, because I could also pick the vertices 1, 2, 3, 4, 5, 6 in the reverse order. Same set of vertices, just the order in which I picked them can be flipped back and forth, and the starting point. So I mean, it's just symmetries of the cycle, right? I've got these rotational symmetry and this reflectional symmetry. Okay, I don't know, rotational and what's the symmetry of like going left versus going right? It's not reflection. I don't know. It's whatever. Van, I think chiral, really? Yeah, let's go with that. Sure. I don't know this word, but maybe. Yeah. So Van, rotation was the j, right? Because there's j ways to rotate it, which is, yeah, exactly. So the number of ways to pick this set of vertices is this quantity here. And then once I pick that, there's p to the j probability that I actually got the red edges in doing that. Okay. And then again, this was for j here. So what values can j take on and be problematic for me? Anything from 3 up to g minus 1, because I want to count short cycles. Those are all the ones less than g. Okay, so it turns out, so let's say let x be the random variable that counts the number of short cycles. Then this all means that the expectation of x is exactly the following. Sum j from 3 up to g minus 1, and then multiply it by the number of candidates for cycles, 2j, times the probability that I get that cycle. Okay. I don't want to dwell on expectation too much more here, but why is this the expectation? You can rewrite the expectation as the sum of indicator variables. Okay, that's the expected value of each of the individual cycles. The expectation of an individual cycle is merely the probability of that individual cycle occurring. Okay, so I would break this up into a smaller sum that would sum up over every possible candidate for a cycle of length j, which is this quantity, times the probability that those j vertices in that order give a cycle, which is this quantity here. Okay, so this is exactly the expected value of x. So this is the average number of short cycles we expect to get through this procedure here. This quantity is too burdensome to work with. So we do what we always do in probabilistic proofs here. We overestimate, often very grossly, but as long as we get something that's good enough for our purposes, it's okay. Okay. So this type of like asymptotics or asymptotia is a skill that's worth developing here as we go on. That's something, again, we'll do. Don't mean for today to be like this big advertisement for my graduate course, but anyway, if you like this stuff, we will do this kind of stuff. Okay, so let's estimate this in a couple of rounds here. So j equals 3 up to g minus 1. I'm going to replace the top with just n raised to the jth power, right? I have j terms in n. Yeah, they're getting smaller, n minus 1, n minus 2, down to n minus j. But certainly they're bounded above by n to the j. And even keep in mind here that g is like a constant. It's given to me in advance. It's 10, a trillion, a billion, and n is as large as I want. So even though this term down here, n minus j plus 1, is getting large, it's subtracting relatively large j, n is way beyond it, right? N is a moving variable, okay? I don't even know if we probably don't even need the 2j part on bottom, almost certainly not, because this is just a constant, right? N still outpaces it, and then times p to the j. Okay, and this equals j from 3 up to g minus 1. I really left 2j? Yeah, why not? Why not? 2j, and then we get on top n to the j times t. Yes, okay. Why is that? Remember what p is. P is 1 minus t. Okay, 1 minus t raised to the j, or let's look at it this way. We have n p all raised to the j. N times p is n times n to the 1 minus t. So, wait, I feel like there should be a negative sign here. Oh, it's not 1 minus t. It's not 1 minus t, right? 1 minus t would be bad. That wouldn't be a probability. T is smaller than 1. It's t minus 1, right? I'll write it like this, right? P is t minus 1. So n to the t minus 1 times n is n to the t. And then I still got the j there. So it's n to the jt. Okay? All right. And let's continue this. This guy here is at most. Okay, this isn't what's in my notes here, but it doesn't matter here. Let's say that this is at most g times n to the jt. Right? Why this? I just dropped the denominator, obviously made it grow. And then how many terms are in this sum here? Oh, okay. I see. I shouldn't write it that way. That's nonsense. Sorry. Yeah. Okay. Let's just say this then. I don't want to write. Oh, yeah. Okay. This is fine. So let's say this is at most. There's g terms in the sum. There's less than g terms in the sum, but at most g terms in the sum. I'll drop the numerator, and then this thing here is of the form n to the j times t. The biggest that j can be is all the way up to g minus 1, or let's say all the way up to g. So let's say the biggest it can be is n to the g times t. Everybody agree this is definitely an upper bound, right? I've replaced each of the j's with g, which is even bigger than it can actually get to. And this is strictly less than what? Oh, actually, let's not even say what it's strictly less than. Let's just make an observation here. So this quantity here, I'm going to say goes to 0 as n goes to infinity. Why is that? Anybody see why this goes to 0? Remember t is less than 1 over g. So I have n to the, wait a minute, that doesn't go to 0. Okay, maybe I was too crude here. Yeah, I was too crude. That's okay.
Isn't g times t less than 1?
Let's see, g isn't less than 1, right?
G times t.
G times t is less than 1, but then I have n to the something less than 1, but that doesn't go to 0, right? That's like n to the 0.001 or something like that. That actually goes to infinity. So instead of, I'm going to put g minus 1 here instead of g, which was perfectly valid because the final value that j can take on is g minus 1. That's the biggest it could be. And I think this will work here because then let's just do a step here. We don't actually need this last computation. I mean, we can just sit there and observe that this thing here goes to 0, but let's rewrite it like this. And then I've got g, and then we've got n to the g times t minus 1. And this goes to 0, right? So g to the t is less than 1. So this is n to a negative exponent, right? So g times t is less than 1. So n, okay, let's say, so g times t minus 1 is less than 0. And this means that we have n to a negative exponent. So this goes to 0 as n goes to infinity, right? N to a negative exponent is 1 over n to the something. As n gets large, we're dividing by a bigger and bigger and bigger thing. So it goes to 0 there. Okay. All right. Right. And so this boxed part here, this is by the definite, right? This is equivalent to t is less than 1 over g, which is given, like that's the definition of t, right? This box thing follows from the definition of t, okay? So this was why we chose t to be smaller than this, so that this thing went to 0, okay? So what does this mean? Okay, what does this mean? This means that the expected number of short cycles is this quantity here, which as n gets larger and larger and larger, gets smaller and smaller and smaller and smaller, okay? So the average number of short cycles starts to vanish as n gets large. Why does that make sense? Let's think for a second here. Why does that make sense? Well, it makes sense because as n gets larger, yes, I get more vertices and therefore more pairs of vertices and therefore more candidates for edges. But at the same time, the probability is vanishing. Probability gets smaller as n gets larger, right? And somehow that probability factor is winning. It's winning the game of making it so there are few cycles, okay? Despite the fact that we tend to 0 cycles, we can't guarantee that we get 0 short cycles. That's not possible. So what we're going to actually do here is say, oh, wait, what? Ah, I didn't even need to do that. That's funny. Okay, so it's not even important that this go to 0, it turns out. So what I want is the following: that the expectation of x divided by n goes to 0. That's clearly true as the expectation itself goes to 0. But actually, if I'd done my old computation with g to the t here, then I wouldn't have gone to 0. I'd been of some sublinear term. That divided by n would have gone to 0. All this tells me is I can play, like I can get away with a little bit better t's here, but it doesn't help me. What I want to conclude is that the expectation divided by n goes to 0 as n goes to infinity, because this allows us to use basic fact number 1, or the first theorem of probability, Markov's inequality. Okay, if you haven't seen Markov's inequality before, that's fine. It's not something I expect you to know, but it says the following here: the probability of a random variable x exceeding a is bounded above by the expectation of x divided by a. Okay, that's Markov's inequality. Okay, it just says that here, and we're going to apply it here to the case, by the way, if expectation of x over n goes to 0, then expectation of x over n over 2 goes to 0. Like whatever, right? If introducing an additional constant there doesn't change anything. And so we're going to apply Markov's here. So this means that the probability that x is greater than or equal to n over 2, so a equals n over 2, is bounded above by the expectation over n over 2. So this is Markov's with a equals n over 2 in this case. This one goes to 0. So it means that the probability that the expected number of, not the expected, the probability that the number of short cycles is greater than or equal to n over 2, this can be made as small as I want if I make n large enough, right? This quantity here goes to 0 by Markov's inequality. So I can make it say less than 1/2 if I want. I can say something way stronger than that if I want, but this is good enough for my purposes, okay? And not only that, I can actually replace n over 2 here with practically anything I want, but this will be good enough here, okay? So through Markov's, I can conclude the following here. And actually just intuitively, it makes sense, right? We just concluded that the number of short cycles vanishes. Like as n gets larger, you have fewer and fewer and fewer short cycles. And all my claim is that the probability that I have greater than or equal to n/2, n being the number of vertices, short cycles, is less than 1/2, okay? But I can replace this 1/2 with any tiny 1 over a trillion if I want, and it's still true because it tends to 0. And I can change n over 2 actually to a smaller value and still get less than 1/2 here. But this is good enough. Okay, this is good enough for our purposes. Why is this good enough? I'll tell you why. The reason is we're going to construct a graph and we're going to have fewer than n over 2 short cycles in it. And I'm going to destroy all of them by removing a single vertex from each, thus losing potentially n over 2 vertices from my graph. But my graph had n vertices, so I still have n over 2 vertices, and that's going to be good enough for me, okay? So this is very ham-fisted here. The probability of it being less than 1/2 is important too, because I'm going to have 2 events I want to happen or not happen simultaneously. Did I get the order right? Yeah, okay, good. All right, so we resolved something about the cycles. Hold on, am I back? Okay, looks like I'm back. We resolved something about the cycles. Now let's figure out the other parameter, the independent sets, okay? All right, we should have time for this. Let's keep this one in mind though. I'll have to scroll back up to it later, but okay, independent sets. Now I want to estimate my independent sets. So first thing I'm going to do is put R equal to the following number. 3 times natural log of n divided by p, ceiling. Okay, R is just this number, whatever it is. Okay, there's a little bit of a magic. You'll see why this quantity works here, but that's why. And this implies, just because we're going to use it in the following form, this implies that P times R is less than or equal to, well, no, sorry, greater than or equal to 3 times log n, right? Just take away the ceiling there, the inequality goes this direction, and then multiply both sides by P. And actually the real form we're going to want to use it in here is the following, that this implies that negative P times R is less than or equal to negative 3 log n, okay? So we need this thing here, okay? We'll see why later on. Okay, so now I want to compute the following. What's the probability that my independence number, alpha of G, so G is the graph produced by this random thing, right? You do an experiment and you get a G out of it. What's the probability that my independence number is at least R? So that I have an independent set of size R or potentially greater. I want to know this probability here. Well, let's give an upper bound on it in a very, very simple way. So here's G, right? And then in G, I can zoom in on a set of R vertices and say, hey, is that independent? If it is independent, then my independence number is at least R, right? So I can check each of these R sets for whether they're independent or not. If I have I'd also have to check even larger sets, but the fact is if there's a set of size R plus 10 that's independent, then it contains sets of size R that are independent. So I just need to examine the R sets here. Now, this one being independent, it gives you information about whether this other one is independent or not. So these events are not independent events in the probabilistic sense. So I'll just use a simple union bound. Again, this requires a little bit of probability. So if you're not familiar, you just have to take my word for it. But there's a reasonable intuition here that this probability is bounded above by n choose R. That's the number of candidates for a set of R vertices. What's the probability that a set of R vertices is independent? What's the probability that this set of R vertices is independent? Right, the probability there's no edge among those vertices. That's what it means to be independent. Anybody?
That'd be like 1 minus p to the R choose 2.
Good, very good, Ethan. 1 minus p, that's the probability of a non-edge. And I need a non-edge for every pair of vertices in there. So raised to the R choose 2. Right, that's the probability that everything in there became independent. And I've got n choose R opportunities for that to occur. Now it's only an upper, not equality here because again, these sets overlap each other. And so they're not independent events, but the union bound still gives you an upper bound here. The probability is actually truly smaller than this. Okay, so now let's do a little bit of arithmetic on this. This can be bounded above by n choose R is certainly no larger than n raised to the R, right? N choose R is something like n minus 1, n minus 2, all divided by R factorial. I just throw away the R factorial from the denominator and replace n minus 1, n minus 2 with n to the R. Pretty crude estimate there. And then I'll write 1 minus p. I'll write this as R times R minus 1 over 2, right? That's just the binomial coefficient written out. And then this equals n times 1 minus p, n minus 1 over 2, all raised, sorry, that's not an n, r minus 1 over 2, the whole thing raised to the r, right? I've got n to the r and a 1 minus p to the r. Just simplify things a little bit. And then this is at most. So the whole thing will still be raised to the r. And then I put n there, and then I'm going to do the following estimate. This is extraordinarily common in probabilistic method. We know that for all p, 1 minus p is at most e to the negative p. Okay, we can use this inequality here always. Actually, we're only interested in it when p is small, but you actually learn this in calculus, right? This is like local estimate. This is a, what, there's a name for this, linear approximation, right? If you look around e to the negative p, it looks like a straight line, which is what this guy gives you here. It's a good estimate. So, and this actually works very frequently in probability. So I'm going to replace 1 minus p with e to the negative p. Okay, so that means I'll get e to the negative p, but that's replacing this. There's still this exponent here. So then it's times r minus 1 over 2, right? And then the whole thing to the r. All right. Let's continue to do the calculation. A lot of textbooks or writings of this kind of skip over this stuff, but I'd like to see why we get the numbers we get at the end here. So now let's rewrite this as n to the, then we've got e to the negative p r over 2, right? Just multiply this thing out here and then times e to the positive 1/2. Sorry, positive p half. Yeah, all raised to the r. Okay, right, I just wrote out this thing here. When I multiply this out, I get negative pr over 2 and then plus p over 2. And when you have a summation in the exponent, it's just the product of the two things there. And then this can be rewritten as, what do we got here when we multiply all this business out? Why do I have it like that? Weird. I don't know where my n exponent went here. Or my r exponent. Okay, it's fine though. So we've got n. Okay, so now let's use, remember we discussed what negative PR is? Let's scroll up a little bit here. Negative PR is bounded above by this thing here. So since I'm making upper bounds, I can replace the exponent of negative PR with negative 3 ln. So we've got e to the negative 3. There's still this extra 2, so 3 over 2 ln n. And then times e to the, I'm going to replace p over 2 with just 1/2. Clearly an upper bound. P is bounded above by 1, so let's put 1/2 instead. And then all of this is raised to the r. Okay, and now we're almost there because now I've got n. So here's why I chose r to be log n, right? I've got e to the log n. Those things cancel with each other, and this brings down n to the negative 3/2. And then I've got e to the 1/2, and all of this raised to the r still. And now in the final step here, I've got n divided by n to the 3/2. And this, it's not important. I've got e to the 1/2. This simplifies to e over n, all raised to the r. Okay, and this goes to 0. It doesn't even matter what r is. R actually does depend on n, but it doesn't matter, right? Because e is a constant divided by n. Like as n gets large, it goes to 0, regardless of whether I have an exponent there or not. That just makes it go to 0 even faster. Okay, so as n goes to infinity. So now, what does this say? This says that we can make the probability that my chromatic number, my independence number is greater than or equal to r. I can make that get extraordinarily unlikely. Okay. In particular, I can make it happen with probability less than 1/2. Okay. So, i.e., for n large enough, gives the following: that the probability of alpha of g is greater than or equal to r is strictly less than 1/2. I can make it as small as I want, but I can definitely make it smaller than 1/2. Okay, and so now the final step of the proof basically is now choose n large enough to guarantee 3 things. The first is to guarantee that r is less than n over 2k. Okay, what's 2k? 2k, k is the desired chromatic number. Okay, k was the number given to us very early in the beginning. What's n? N, I mean, what's r? Sorry, r is something like 3 log, 3 ln n ceiling, and n is just n. Does everybody agree that n large enough, eventually the right-hand side will dominate the left-hand side? The left-hand side is growing as fast as log n. The right-hand side is growing as fast as n, order n. And the fact that it's divided by 2k, well, k is a constant. So this guy will eventually win, probably very quickly because log n's small, but we can choose n large enough so that that happens. Okay, that's the first thing. That's the least interesting, or I mean, I don't know. The second one is we can guarantee that the probability x, this was the number of short cycles, being greater than or equal to n over 2, has probability 1/2. And we can guarantee that the probability that the independence number of the graph that I'm picking, so this x is a property of G as well, greater than or equal to R, is also less than 1/2. Okay. Now, if we can choose n large enough so that the probability of these two events occurring is less than 1/2, then it means there's a non-zero probability that both of these fail, right? Because both have probability less than 1/2, then the probability of them both occurring is less than 1. So there exists positive probability that neither occur here. Okay. Non-zero prob that x is less than n/2 and alpha of g is less than r. Okay. So the not of these two things is you want neither of them to happen. That one or the other happens is with probability less than 1, because the sum of these is less than 1. So the probability that they both fail is greater than 0, right? Non-zero probability that these two happen at the same time. What does that mean? That means that so there exists a G with less than n over 2 short cycles and alpha of G less than R. Right, that's the key fact of the probabilistic method. That if the probability is non-zero, then it has to exist. Because keep in mind, what is the probability space? It's every graph, right? On n vertices. I've got n vertices and I flip coins for each of those edges. Every single graph exists in that probability space. Some are less likely than others, obviously, right? With a small probability, a complete graph is very unlikely, but it has a non-zero probability, so it's there. Any kind of graph exists with whatever probability, it's there. In particular, any graph with non-zero probability is there. Here's a graph I just described to you with non-zero probability. Now this almost has what I want, right? Why does this happen? I mean, why does this give me what I want? The final step is now construct a new graph G star by removing a vertex from each short cycle. Okay. The number of vertices, therefore, in G star is at least n/2. G has n vertices, right? And it has strictly less than n/2 short cycles. So I'd need to delete at most n/2 vertices to destroy all those cycles. Okay. What about the independence number of G star? It remains less than R. If I have independence number less than R, so no independent set of size R, and I remove a vertex, can my independence number go up? Can I produce larger sets of independent vertices? No way. Things don't become independent because I removed a vertex, right? That vertex might have been independent and it got smaller, but if it's there and I remove it, there aren't other vertices that now don't have an edge between them, right? That had nothing to do with it. That got removed. So alpha of G star is still less than R, and that's less than n over 2 times k, right? That was one of the reasons we chose R to be large enough. And therefore, the chromatic number of G star is greater than the number of vertices of G star, which is n over 2, divided by the independence number, which is n over 2k at least. And this is this comes out to be k. Okay. And so now look at G star. G star has no short cycles. We destroyed them. We literally removed a vertex from each short cycle, so there's no short cycles. Okay. So G star has girth greater than or equal to G. Actually, I think we got strictly greater than G here. The way we set it up doesn't matter. And its chromatic number is actually, it's strict here again, strictly greater than K. And this is which is what we wanted, right? G star has our property. Okay. This is called the alteration method. The graph produced by the random method did not quite have our property. The graph, we altered it to a new graph G star that did. Okay. Now there are some improvements here. Like we actually could have made sure that the number of short cycles here was as small as we wanted. Like we could have made it be smaller than n over a trillion or even non-linear, but like it didn't matter. We still deleted vertices to get rid of them. We have to delete some short cycles. We can't guarantee no cycles. That the proof will not work this way to guarantee to make the probability of no cycle. That's not possible. There do exist graphs like that. You just can't start. You can't get them probabilistically. You have to do this deletion trick. And anyway, changing this aspect here isn't the sort of key factor. Actually, it's one thing worth thinking about for a little bit is which of these has the strongest pull on the size of n, and which of these two like things where we did independent sets and cycles, which of those had the biggest influence on p? One of them controls p a little bit more than the other one, and then the other one you kind of get for free. Okay, but those are just thoughts about it. Those aren't integral anymore to the proof. Okay, so that's the end of it.